Hello everyone, my name is Aimée Ogando and I am going to be presenting my Physics 2211 Lab 5. The objectives of this lab are to model the motion of a stretched slinky dropped from static equilibrium, use Tracker to extract data to analyze the motion of the slinky and use GlowScript to predict the motion, and compare the predicted and extracted motion of the slinky and discuss its findings. The problem that this lab intends to answer is what are the differences between the observed and predicted motion of the falling slinky. My hypothesis for this problem is that the observed motion of the falling slinky shows much more discrepancies between its values because it takes more factors into account than the predicted one using a computational model. The fundamental physical principle involved in this problem is Newton's second law. This law is also considered as the law of motion because it describes the behavior of objects for which all forces are in balance. It tells us that the net force of an object is equal to the mass times the acceleration, where the net force and acceleration are vectors, saying that the acceleration is equal to the ratio between the change in velocity, a vector, and time, and distributing this change in velocity vector times the mass, knowing that the mass times the velocity equals momentum, we can say that the change in momentum is equal to the net force times the change in time. As well, this experiment takes into account the drag force, also known as air resistance or friction, which is the force acting opposite to the relative motion of the system. This force can be found by multiplying the negative proportionality constant by the square speed of the object and the velocity direction. The gravitational force is the force by which the mass of planets or objects are attracted to each other. This is found by multiplying the negative gravity of the system times the mass in the direction of the gravity. These are the variables and materials used in this experiment. This is the procedure followed to do this lab. And this is the video of the experiment where you can see the slinky falling from a man's hand. Highlighting the most important parts of the computational model, we can see that I first determined the mass of the slinky as given, then identified the initial velocity and position of the slinky extracted from Tracker, and the value of the time step used in Tracker. After that, I just identified the value of the magnitude of gravity, determined the direction of the motion of the slinky, and then identified the proportionality constant of the drag force of the slinky. After that, I determined the condition of the while loop with the duration of the movement of the slinky and calculated the working force of the motion. Using the velocity and position update formula, I recalculated the velocity and position of the slinky and then redefined the change in time of the motion frames. After that, I determined the condition of the while loop with the duration of the movement of the slinky that would take into account the drag force. With that, I calculated the net force and the drag of the motion, and using the velocity and position update formula, I recalculated the velocity and position of the slinky and then redefined the change in time of the motion frames. This graph shows the observed and predicted motion of the bottom of the slinky shown in the video, taking only into account the forces on the y direction. We can see that at the beginning of the graph, both motions behave to a certain extent similarly until about 3/4 of the motion, where we can see both motions plummeting. This happens because the slinky has finally caught up or aligned with the bottom of the slinky and begins to fall at a rate similar to the force of the gravity. In this graph, we can also appreciate that the observed motion deviated more from the average values than the predicted one because this is one that is more exact and doesn't take into account other factors like other forces acting on the environment. Some interpretations that can be drawn from this experiment is that the observed motion shows more fluctuations because it considers forces the predicted motion doesn't, like the drag force and the x-force. As well, we conclude that we can use the Newton's second law to predict an object's motion when the net force is not equal to 0, considering more than one force is acting on the object. I would like to note that this experiment did not take into account marginal errors like the cross-directional wind in the x-axis, and this may have occurred some systematic errors like only using 27 frames. And going further into the discussion, if we ask ourselves why does the bottom of the slinky stay stationary, we can say it is because the forces acting on the y direction cancel out until the top of the mass reaches the bottom and there is no more tension, and the bottom of the slinky oscillates slightly but has net zero displacement until the entire slinky reaches the bottom. And if we want to integrate the energy principle in this experiment or in this discussion, we can argue that if the energy principle is satisfied, and I believe it is not, because there is a non-zero change in energy due to an increase in kinetic energy when the slinky is dropped, which doesn't allow there to be balance or equivalent forces of the slinky in some moments of the motion. So that would conclude that the energy principle is not satisfied from my observational model. Thank you for your attention.